us understand radius of gyration. What is radius of gyration? Radius of gyration is when we have moment of inertia of a body about some axis which we have got probably through integration etc. Let's say about yy dash, we have found the moment of inertia of this body of mass m. How we have found it? We break it into smaller pieces. Differential element of mass, we say this is particle of mass m1 at a distance r1, this is a particle of mass m2 distance r2, and then we say summation of m1 r1 square plus m2 r2 square and through so and so on. When we integrate it, we get the moment of inertia of this body about this axis, right? So this way we find the moment of inertia of a distributed mass system about some axis. So what do we mean by radius of gyration? Radius of gyration means that is if we collapse this body, if we condense this body into a particle of the same mass. So now this body has been converted to a particle. This particle has suppose a distance x from here, and if the moment of inertia of this body about this axis is same as of this particle at a distance x, then this x is called radius of gyration. Let's understand it by an example. Over here, this is a rod of mass m, length L. Yy dash is passing through its center of mass and perpendicular to its length. This is a thin rod with a uniform linear mass density. About this axis, we know that is moment of inertia Iyy dash is ml square by 12. This is the moment of inertia. We know that is how we derived it in our earlier lectures. Through integration, we had found it as ml square by 12. Now we are interested in finding the radius of gyration, which is known as k. Radius of gyration. So obviously the dimension is m0 l1 t0. Dimensional formula is this, and unit is meter only. SI unit is meter only. Now if we have to find the radius of gyration of this rod about this axis, then number one, we condense it, we collapse it, that is we convert it to a particle of same mass. Mass should be same. And we keep it at a distance, suppose this is a distance k. And now if the moment of inertia of this particle of mass m about this axis is same as the moment of inertia of this distributed mass system of this axis, then this distance is going to be called as radius of gyration. If we increase the distance, we keep this mass over here, then the moment of inertia of this particle about this axis will be more as compared to original moment of inertia of this rod about this axis. If we reduce the distance very much, then the moment of inertia of this particle of mass m about this axis will be much lesser as compared to the actual moment of inertia of this mass distribution about this axis. But there is going to be some distance, let's say this k, over where when we keep this particle of mass m, then the moment of inertia of this particle about this axis is equal to the moment of inertia of this mass distribution about this axis, then this k is going to be called radius of gyration. So now how do we find radius of gyration? It is very simple. You just find the moment of inertia as you had been finding about this axis, about any axis, you have to find the moment of inertia. So about any axis which you have been asked for to find radius of gyration, about that axis using integration, parallax theorem, perpendicular theorem, etc., you will find what is the moment of inertia, and simply put it is equal to mk square. Like over here, Iyy is ml square by 12. Now you have converted to the mass particle system, and let's say this is the radius of gyration, mk square. So the moment of inertia of this particle about this axis is mk square. So by the very definition of radius of gyration, this moment of inertia should be equal to this. That is, when ml square by 12 is equal to mk square, m and m they get cancelled. So k comes out to be L by root 12 meter. This is going to the answer. So when we say k is equal to L by root 2, this is the radius of gyration for a rod of mass m, length L, uniformly distributed mass about an axis passing through its center of mass and perpendicular to its length. Similarly, we can find the radius of gyration for other bodies. Let's take few examples. Let's say this is a solid sphere of mass m, radius r. So Iyy dash is moment of inertia about diameter. We know it is 2 by 5 mr square. If we have to find the radius of gyration for this distribution of mass, we simply put it as equal to mk square. Mass will remain same. So 2 by 5 mr square is equal to mk square. M and m they get cancelled. So root t by 5 r is equal to k. If we have axis over here, let's say now we have axis over here, we have taken I dash, and let's say we over this we call it as ICM, that is moment of inertia about this axis. We know it is 2 by 5 mr square. This is 2 by 5 mr square and this distance is x. Now if we have to find the radius of gyration of this solid sphere about this axis, so the first thing what we do is we find the moment of inertia of this solid sphere about this axis. Using parallax theorem we can find it, and then directly we put it is equal to mk square, where k is radius of gyration. We can get the answer. Like over here in this case, we know that is Iy dash is equal to ICM plus m into x square, that is parallax theorem, where m is the mass of the body and x is the distance between these two parallaxes, and we know this axis is passing the center of mass, so we can very well apply parallax theorem. So Iy dash is going to be equal to ICM is what? It is solid sphere 2 by 5 mr square plus this is going to be mx square, m into x square. So Iy dash is known, Iy dash is known. If you have to find the radius of gyration, so what we do is we directly put it is equal to mk square. So 2 by 5 mr square plus mx square is equal to mk square. M they get cancelled. So 2 by 5 r square plus x square root is going to be radius of gyration for this distribution mass system. Similarly, you can find the radius of gyration of any distribution of mass about any axis. First you find the moment of inertia about the required axis, then you put that moment of inertia which you have got using parallax theorem, perpendicular theorem, or through integration, etc. You directly put that moment of inertia is equal to mk square, and this k stands for radius of gyration.